Newton's laws of motion. All right, first I want to define for you what a force is. And a force is defined as a push or a pull. The SI unit we use for force will be newtons, or capital N. And a force is a vector quantity, which means a force will have a magnitude or a strength value, but it also will have a direction. Okay, now Newton's first law of motion. Newton's first law of motion is basically Galileo's law of inertia refined. Galileo's law of inertia says that objects resist changes in motion. In other words, if an object is at rest, then it will want to stay at rest. And if an object is in motion, it will want to stay in motion at a constant speed in a straight line. The more mass an object has, the more inertia an object has. In other words, the more mass an object has, the harder it is to get an object to change its motion. For example, to make an object move once it's at rest, or to change an object's velocity, change direction, or to go faster or to slow down. So the more mass something has, the more it will resist any changes in motion. Newton refined this idea by saying an object at rest will stay at rest, and an object in motion will stay in motion at a constant velocity unless acted upon by a net force. This is written slightly different on page 74 of your textbook if you'd like to see it written just a slightly different way. For example, objects in flight on Earth eventually come to rest because of two different net forces acting on them. One is the force of gravity, and the other is the force of air resistance. And it is because of these two net forces that objects will come to rest. If these two forces were not in existence, then an object in flight will just continue on in a constant velocity. All right, now I would like to distinguish with you the difference between the terms mass and weight. First of all, the definition of mass is the amount of matter within a substance, and the SI unit we use in physics for that is the kilogram. Weight, on the other hand, is the amount of matter in kilograms multiplied by the acceleration due to gravity in the unit of meters per second or meters per second squared. So the weight of an object is equal to mg. So the value for g varies depending on where you are in the universe. On Earth, we have a value of 9.8 meters per second squared. There are places in the universe where there's no gravitational force at all, or g is 0 meters per second squared. So in those places, your weight is also 0. Or if you're on the moon, for example, where your acceleration due to gravity is about 1/6 of what it is on the Earth, then your weight value will be about 1/6 on the moon than what it is on the Earth. The unit for weight is the same unit for force, since weight is considered to be a force. So the SI unit for weight is the Newton, and that's also equal to the unit for mass, which is kilogram, multiplied the unit for the acceleration due to gravity. In other words, 1 Newton is equal to 1 kilogram times a meter per second squared. All right, it's now time for Newton's second law of motion. Newton's second law of motion is the sum of the forces acting on an object is equal to the object's mass multiplied by that object's acceleration. For example, let's start by investigating Newton's second law of motion by drawing something called free body diagrams. A free body diagram looks at an object. In this case, let's say we have a block resting on the ground. It looks at one object and it identifies all the forces acting on that object. In this object, it is at rest and there are only two forces acting on this object. I always start at the center and I draw a little dot. And the first force acting on this object is acting downward, and this is called the object's weight, or W. There was another force acting on this object, and that is from the ground pushing up on the object, and that is called the normal force, or what I write F sub n. According to Newton's second law of motion, if I added up these forces, they should be equal to the mass of my block multiplied by the acceleration of my block. Let's go ahead and make upward positive. And if I apply Newton's second law of motion, my first force, which is the normal force, is positive or upward, minus my weight because it's acting downward. And I'm going to set it equal to the mass of the block multiplied by that block's acceleration. Now, if I'm solving for, let's solve for the acceleration of the block, let's say, then all I need to do now is divide both sides by the mass of that block, and I have an expression for the acceleration of the block. Here's an example. Say you have a block at rest on the ground, and this block has a mass of 1 kilogram. Using Newton's second law of motion, find the normal force of this block. Alright, well, what is the information that we have? The object is at rest, so the acceleration is 0 meters per second squared. We know the mass. We can make upward positive. The next thing we need to do is draw a free body diagram. So we will draw a little dot in the center of my block. And there are two forces acting on this block. One is down and one is up. The one down is the weight of the block, and the one acting upward is the normal force. Now, if I apply Newton's second law of motion, the formula is the sum of the forces is equal to ma. Rewriting this, that would be the normal force minus the weight, or mg, is equal to ma. Now, the acceleration is 0. And so if we plug in 0 in this formula, we know that 0 times anything is 0. And if I add mg to both sides, I see that the normal force is actually equal to the weight. And the weight is 1 kilogram multiplied by 9.8 meters per second squared, and that gives me an answer of 9.8 newtons, or 9.8 kilograms times meters over second squared. That's otherwise known as 9.8 newtons. So what I like to say here is that if you're on the level plane, which we are in this example, if you're on a level plane, then the normal force and the weight can be the same. All right, now Newton's third law of motion. If one object exerts a force on a second object, the second object exerts an equal force in the opposite direction of the first. This is also known as the law of action-reaction, or pairs. Whenever there's an action, there's an equal and opposite reaction. Let me give you an example of this. Again, let's have the ground, and this time we're going to have two blocks here. They're tethered with a rope between them. And there's a rope in the front where someone or something is pulling on this rope. So there is an applied force. Something is pulling on this rope. When we have something pulling on this rope, the first block, we'll call this one the first one, and this is the second. The first block will feel a force of tension pulling on it because of block 2. And since we have two objects, then it turns out the second object will feel a force of tension from the first object. According to Newton's second law of motion, this force of tension is equal in value, or we would say equal in magnitude, but as you can see in the picture, they are opposite in direction. All right, let's do some practice. So let's have a diagram here. We're going to again have two blocks with a rope between them. This will be object 1, object 2, and there is some applied force pulling these two blocks to the right. There are 6 more forces on this diagram below. Go ahead and try and sketch those out. I'll give the answer shortly, give you a few moments. Okay, let's get some going here. We have the weight of object 1, and we have the weight of object 2. We also have the normal force of object 1. We have the normal force of object 2. And we also have the force of tension between them. All right, more practice. An object with the mass of 10 kilograms is at rest on the ground. Using Newton's second law of motion, find the normal force. So here's the object, and the answer, well, I'll be putting that up shortly here. Okay, there's your answer, 98 newtons. Alrighty, last problem. Draw the two forces on the block hanging from the ceiling. What is the mass of the block if the tension in the rope is 10 newtons? So here I have a ceiling. I have a block hanging from a rope from the ceiling. You'll need to draw the free body diagram on this block and then determine the mass. Here is the answer. The mass is approximately, this is approximation, so squiggly line here, approximately 1 kilogram. The end, or I should say bye for now.